Hi everyone, I'm Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today we're going to study what is MOS capacitor. MOS capacitor stands for metal oxide semiconductor capacitor. So particularly it is an integral part component of MOS transistor. So let us see. So what is the today's overview of today's presentation. So let us start with introduction to the MOS capacitor and basics construction of MOS capacitor and its operation and its characteristics. So and then conclude with the summary. So coming to the constant introduction part, MOS transistor stands for metal oxide semiconductor. So a MOS capacitor comprises a semiconductor, let us say body. So complete body of the MOS capacitor consists of a semiconductor body or substrate, and also an insulator film. So you can say this one, semiconductor body or substrate. So substrate means it can be used as a insulator, dielectric material. So then insulator film such as SiO2 and a metal electrode called gate. So actually in olden days, so let us say 1970, before 1970, a metal element is used in the case of to have a terminal gate terminal, right? So after that, so we have used aluminum type. So we can say here after 1970, heavily doped polycrystalline silicon has been the standard gate material. So previously before 1970, so as far as this gate terminal to form the gate terminal, so metal is used, for example aluminum, hence the name metal oxide semiconductor. So after that silicon, the polycrystalline silicon has been replaced with that metal, even though the name has been continued same metal oxide semiconductor. See here comes to the oxide film. So oxide film can be as thin as 1.5 nanometers. 1 nanometer equals to 10 angstrom. So very thin. So very limited portion of the total MOS capacitor. The size of a few oxide molecules. So very light portion will be the minimum portion of the total MOS capacitor. So therefore, because of its ability to withstand high temperatures without reacting with SiO2. So why this polycrystalline silicon has been replaced with metal means because it has it can have high temperature resistance. So it can withstand high temperatures also. So robustness. So that's why so sometimes if temperature increases, it changes its states. So the properties of the particular material can change with temperature. In such case, there may be a chance of chemical reaction with the other components. So therefore, because of that reason, but polycrystalline silicon has been standard gate material because of its ability to withstand high temperature without reacting the silicon dioxide layer. So therefore, in place of metals, we can use polycrystalline silicon. So it is used in integrated circuits, MOS transistor. This is the actual basic advantage or application of MOS capacitor. So it is not used individually, MOS capacitor. So it is the integral part of the MOS transistor. So in MOS transistor, particularly to store charges in ICs, integrated circuits. The capacitance of MOS capacitor varies with voltage applied to its gate terminal, with body typically grounded during this application. So this is the basic idea of MOS capacitor. So the basic principle is the MOS capacitance. Capacitance of MOS capacitor varies with the voltage applied to its gate terminal. So that is the basic principle. Okay. So we can control the voltage capacitance. So capacitance is proportional to the applied voltage across the gate. So coming to the construction of MOS capacitor, you can observe here. So this is it consists, MOS capacitor consists three different layers. Metal, so metal means just now polycrystalline silicon we have to use, and then oxide layer, then you have a semiconductor material. So make semiconductor maybe P type or N type. So this is MOS cap, it can also be represented termed as MOS cap. So this is, let us say, P type semiconducting material. So the terminal is body, and then silicon controlled SiO2 layer, and then thickness of the metal, T oxide thickness, you can say. The oxide thickness is Tox. So it's a three layer device. Metal gate, typically made up of aluminum. So actually aluminum before 1970s. So nowadays they are using polysilicon and polycrystalline silicon. This is the top plate of the capacitor. So this is the top plate, top. And then insulating oxide, a thin layer of silicon dioxide, SiO2, that acts as an insulator. So this part, which is very thin, this is your insulating oxide layer. Next, semiconductor substrate layer, that is usually silicon, which can be either P type or N type. So top layer consists of polycrystalline silicon, and oxide layer is SiO2 layer, silicon dioxide, and semiconductor is also again silicon. So all the three are components of silicon. And in laboratory, particularly these type of MOS capacitors are used. MOS capacitor, discrete type MOS capacitors. So let us see the energy band diagram of MOS capacitor. So here you can observe QSI, Q phi Si. So this is the work function energy of silicon. So because there are three different layers, right? So polycrystalline silicon, and then so you have SiO2 layer, and then you have P type or N type silicon semiconductor material we have to use, right? So that means all these are different materials. So all these have different energy functions. So we can imagine that the work function are different, and then the energy band diagram also looks like different. So here you can observe this is gate, first part is gate, and second part is metal oxide, and so this is metal, first one is metal means polycrystalline silicon, and second one is oxide layer, and third one is semiconductor. So here we have considered P substrate, and this is body, and this is gate, and here at this point we can say x equals to 0. So as x increases towards the x-axis right side, so that they changes the energy band diagram. So here this is first vacuum energy band diagram. So this is Fermi level. So this is first one, we have a metal, no? So this part is metal, and then we have oxide layer, SiO2 layer, and then final one is semiconductor layer. So in this layer we know the energy band diagram between in case of metals, so they overlap, conduction band and valency band, they mixed overlap together. So in such case we can say, so this is D phi silicon, the energy work function, and then phi m is the work function energy of metal, and then Q phi SiO2, that is work function of energy, work function energy of silicon dioxide, SiO2 layer. So three different layers, three different work function energy, and then final Q phi f is the, so here Fermi level, so it represents Fermi level. Q phi f means Fermi level energy function. So it is given by EFI minus EFP, and then so we KT ln P by Ni, so intrinsic electrons, so P, and then holes and electrons are there, so KT ln Na by acceptor concentration by intrinsic concentration. So that is given by here. So all related to the energy band diagram, conduction band and valency band. So here in SiO2, so SiO2 acts as a insulator. So you know insulator has the energy gap between valency band and conduction band is very high. And coming to the, when compared to the metal, for say semiconducting material, the energy band diagram is somewhat little. There is some very less amount of energy band gap is there between conduction band and valency band. So by this way, by changing the properties or by external voltage to this gate and across gate, so we can able to change this energy band, the conduction band and valency band. So now we have to consider few assumptions. We have to make some assumptions in order to analyze this MOS capacitor. First one, SiO2 layer is a near perfect insulator, so dielectric. So that is very important. Okay, SiO2 layer is acting as a pure insulator, insulating material or dielectric, pure dielectric material, so that it can has energy band diagram like insulator. So huge gap between conduction band and valency band. Assume zero charge in the oxide. Electric field is constant and potential is linear in the oxide. That is another assumption. So we had a second one, assume zero charge in the oxide layer. Zero charge because obviously it has insulator. So no charge carriers to move further. And electric field is constant and potential is linear in the oxide layer. So N plus polysilicon has a potential which is the maximum possible in silicon. So N plus polysilicon has a potential. So polysilicon is a metal. So in which, so we have a top layer has potential which is maximum possible in silicon. Next, zero work function difference between metal and semiconductor. This is another important assumption is that, so we have to assume that there is a zero work function between metal and semiconductor material. So this is metal and this is semiconductor material. So in this between, so different work functions, different materials. So we can say, so there is a zero work function between your metal layer and semiconductor layer. Right. So that is about basic construction and operation. So today what we have discussed, we have started with introduction to the MOS capacitor, and we have described what is MOS capacitor, where it is used, and we have discussed its internal structure and its energy band diagram, and we have assumed some few assumptions. We made few assumptions to analyze the operation further of the MOS capacitor. So probably next topic will be operation of MOS capacitor. So with this knowledge, we can able to analyze, we can able to know the operation of the MOS capacitor. Thank you.